but we're not talking about Navier-Stokes. We need something that is with feasible computational burden, efficient, to be used in optimization, preliminary design, dynamics and control. This guy is very efficient, but it's for another regime. We need something that satisfies these two characteristics. Capture the leading edge vortex, or in general, captures in nonlinearity, right? This is a nonlinear. The CL alpha curve is not 2 pi sine alpha. It's not 2 pi alpha. It's not linear. Or not even 2 pi sine alpha. It's something different. Something to capture nonlinearity and unsteadiness. These are the two hard parts. Here is nonlinear, that's fine, but steady. Here is unsteady, but it's linear. This is our course. Over there, it's unsteady and nonlinear, and both cannot be neglected. This is the challenge, okay? So let's recap what we did in our course. So we already know this, right? We know Wagner, that the lift as a function of time, S is our non-dimension of time. It's just the steady lift multiplied by Wagner function. This is Wagner function, right? So it increases up to, so far out in time, steady state, you get the steady value of your lift, whatever it is, okay? So this is the Wagner function. You multiply this value, but the Wagner function, you get your total lift as a function of time. This lift is due to what input? Step, very good. What if I want the lift due to arbitrary time varying input? We have different ways, one of which is to do the Duhman. I mean, this is from system dynamics perspective. This equation is very generic. I mean, it doesn't, you don't need to use W as a Wagner function and alpha as an input. I mean, you can use it with, whenever you have step response, just use it here. For any dynamical system. For any dynamical system, the output due to any arbitrary time varying input is determined from the step output. Okay? This is the interpretation of this equation. This is the step output W, and here is your alpha. So if your alpha doesn't change with time, so this is 0. So you recover that, okay, multiplied by the initial alpha, the step value, times your Wagner as a function. If not, so this is what takes care of it. That's okay, so you can do this. Okay, we can get, this is what you did in your homework. We can get the lift variation due to an arbitrary time varying angle of attack. You did it for the ramp, hold, and then coming back. Some people actually do it with not taking alpha as the input, but u times alpha. If you have u as a time varying, so the speed of your airfoil is time varying, okay? Like for a helicopter blade in forward flight, right? Or for our flapping flight, of course, flapping flight, the wing accelerates and to reach maximum speed and then decelerates to come to a complete stop. Accelerates and decelerates. So if you have a time varying free stream or forward speed of your thing, alpha is not your input. You do it with u times alpha. Okay? And this is the most, the most recent thing is that people, or the most clever thing, most complete, let me say, it's not u times alpha. Is alpha a little bit larger? It's actually u sine alpha. It's not u times alpha. So you use, let me tell you here. So this is the relation that you find in books, all the books, okay? But I mean, if your u is time varying, you pick one of these u squared and get it inside as the input. And if alpha is a little bit larger, it's u sine alpha. Look at this and look at that, and just let me know if you have any questions. This is the thing that you have in books, and this is the thing that Bedus and Leishman use when they have a little bit larger alpha. Okay. If you have any questions, just let me know. Just to give an idea. So I wanna. So this equation is what? This equation is as if you're giving the alpha your angle of attack input to the state space model that we derived, or to Tudorson transfer function, or whatever, okay? This is, we're giving alpha as an input to our flow dynamics to get the lift as an output. Here, we're not giving the alpha, we're giving u sine alpha, okay? as a multiplication. So if you have here, this is alpha, just a particular alpha, that varies between 90 degrees, it's for flapping, between 90 degrees, 120 and 60. So this is alpha, sinusoidal. Sine alpha is the red. Alpha as an input is not the same as sine alpha for larger angles. But more importantly, if u is constant, if u is number 10, when you multiply by sine alpha, that's okay, you scale. But if it's time varying, so for this example, I have this as sine alpha and I have u as a sine wave. If you multiply this by a sine wave, you get this guy. What I'm trying to say is that these three things are different signals. So if you give any of these to our dynamics, our state space model, you will get different output, variation of time, okay? Because they are different signals. This is the point. So which is the most generic? Which is the true thing and which is the makeup or which is the reduced? This is the point here. So again, I'm reminding you of this. This is the u sine alpha kind of thing. What is the problem of using this? Okay, so it seems that u sine alpha is more general than alpha only or u alpha. What's the problem of this guy? What's the problem of using it? Here's the thing. Let's see. This is lift coefficient versus the angle of attack. Steady, okay? This is steady. The dotted is the linear thing, and the blue, the solid here is this is the non-linear thing. The true, let's say. So if I'm giving step change angle of attack 45 degrees, so from 0 to 45, the lift will increase from 0 up to the lift corresponding to 45, right? If you use these formulas, this is what you will get. The lift will increase and reach the value, the steady state value, asymptotically reach the steady state value that is close to 5. So this guy is going to 5 in infinity. But this is the incorrect value. This is the one that you get from the linear theory. Here is the true one. We should see something like this, that the lift increase and reaches asymptotically the true value, right? So what is an unsteady model that can do this for us naturally? This is the point. So here is the thing. Do you remember this equation? This is what do we call this equation? What do you call it? Integral equation for circulation. This is the unknown, right? And this is the input. This is the one that is seen in Tudorson. This is the point. It's all about this equation actually. Why? Because when you solve this equation and you get the response, this is the dynamics of Wagner, Tudorson, or the state space model that we have. Okay? Every dynamics is in this equation. And this is the point. Here is the aerodynamic input. You can see that it can be alpha or alpha 3/4. If you multiply here by u, so it's u times alpha, right? And if you're meticulous enough, so it's actually u sine alpha. So it's as if it all depends on how you interpret the input. Because u is constant, you can multiply it here and there, that's fine. But actually, in the von Karman and Sears formulation, this was the equation. So what is the input? Gamma what? What's the input? What's the input? What's gamma naught? The quasi-steady circulation. So in fact, the most general input to our potential flow dynamics is the quasi-steady circulation. If you realize this, you can immediately rewrite this equation with the quasi-steady circulation being your input. If you do that, here is the modification. It's as if you have rho u times gamma, but this gamma is the one that you get from your unsteadiness. Apply your quasi-steady as the input instead of u sine alpha. Okay? With Wagner, the same Wagner, you get your unsteady lift. That's okay. So why this is better than anything before? Because of the following. Quasi-steady circulation, you can write it as follows. You can write it as a rotational part, that's fine, and translational part, one due to the wing translation. This one, due to the wing translation, what's this? This is quasi-steady circulation. So this is quasi-steady lift, means steady lift. The steady lift is a function of the angle of attack. This functional dependence cannot be anything. It doesn't have to be 2 pi alpha. It doesn't have to be 2 pi sine alpha. You give me whatever unconventional lift mechanism you like. Tomorrow morning you discover a new phenomenon and you have a nonlinear lift mechanism. CL as a function of alpha is exponential of alpha, whatever. And you give me the airfoil motion that you're doing. This model will give you back the unsteady lift that captures your nonlinear lift mechanism in an unsteady fashion. Okay? So we delayed the nonlinearity to the user. You define your nonlinearity here. You give me the nonlinearity is determined from the steady point. Okay? So this is what we did in our model. But if you remember, this formula by itself is not that useful. To have an unsteady model that is really useful, you should write it in what form? What form? Come on, guys. If you want to develop an unsteady model and you want it to be useful to people, you should write it in what form? Laplace. What Laplace? So if I gave you an equation like Laplace square phi equals 0, is it very useful that you can use it? State space. State space, of course. State space 4, right? So all what you did then is to convert this in a state space form. If you use this is what we call the extended Doppler principle that we developed in this work here. And if you use the Wagner function, the same approximation that we had in the class, the issue now is that S is not, S is what? S is the non-dimensional time. So the travel distance divided by semicolon. So this was the travel distance. For a constant u, it's u times t times time. For a time varying u, it's the integral of the speed, right? The distance, travel distance is the integral of speed. When you substitute this here, you have exponential and you have integral. It's a little bit hard, but it's not that difficult. You can just substitute here and play a little bit with mathematics. You can show that the lift actually is written in this formula. These two x's are the two internal aerodynamic states that we have from before, whose dynamics is governed here. It's time varying coefficient now because u might be time varying. The quasi-steady circulation is the forcing input. So these 3 lines is the most general lines, and indeed if I have a problem and I want to be practical, I will go and apply this model. So like I said, you give me the nonlinear lift mechanism you like. CL is steady as a function of alpha, exponential, whatever. Okay, you have this. And you give me the airfoil motion represented by time varying speed and time varying angle of attack. You immediately get the quasi-steady circulation. This is your forcing input to this linear dynamical system with time varying coefficient. The output of it, which is the 2 states, just 2 ODEs. We put them here to get the unsteady lift that captures your unconventional lift mechanism in an unsteady fashion. When we did this on insects, this last slide, so we compare with Navier-Stokes. Navier-Stokes is the black. The green are the classical unsteady, but I try to, if you use the 2 pi alpha kind of thing, I mean the things that we used in this class, the classical will be out of the board. Will give you much crazy lift, fictitious. So we reduced it by using the alpha at the 3/4, and we did a little bit stuff and aspect ratio corrections. So this is the best that you can get out of the classical theory. It's much higher than the true values at the peaks. Why? Because at the peaks you reach actually the large angle of attack, 46. So you don't get that. The blue is the best quasi-steady model in literature so far. So in near stroke reversals, it doesn't perform that well. The developed model, the dotted red, closely matches the CFD results as you can see here. And we cannot aspire for a better solution because actually, remember, this is a very complicated problem. It's three-dimensional, it's unsteady, it's nonlinear, there is a leading edge vortex going on, and this model, you just hit F5, everything pops up immediately, so it's pretty efficient. So this is the best that you can get out of here. So it's all based on the fact that the quasi-steady circulation, because you will not find this in books. So this is what we stressed. But we did not invent it. It's 1938 by von Karman Sears, you know, but it has to be stressed. Here it's stressed in this work, and these three lines are sufficient. You can solve a lot of problems, a lot of nonlinear problems. Okay. I'm done. One caveat here. Anybody can tell me what's the caveat? What's the problem here? Here is the problem. There are two sources of nonlinearity. Nonlinearity in the input-output map. This is your input, this is your output. In the steady state, the map is nonlinear, the function is nonlinear. We capture that because actually the user provides it, right? But there is another nonlinearity. What's the other nonlinearity? It's nonlinearity in the dynamics itself, in the flow dynamics. That the dynamics should depend on the operating condition. So I don't know if I showed this before or not, but for a true nonlinear dynamical system, this is time. If you give a step input, you may get first order response. This is input. What's your input? Maybe the input is 1. Okay? Step input, unit step, your system may be just first order like this. This is the output. If you double your input, if it's pure linear system, it will have the same response. So it will go to double the value. This is input equals 2. If it's linear system, it will go double the value in the same time. Double the value in the same settling time. This is the definition of a linear system. Okay. But for a true nonlinear system, no, it doesn't work like this. For a true nonlinear system, the response may be different and maybe more slower, maybe actually turns to be second order in nature for a larger input, right? And for a larger, even larger input, it may turn to be unstable. Okay? So the dynamics may depend on the value of the input, on the operating condition. In this model, we assume the dynamics